So this is all, good. I covered small model classes, and then this Solarov class, which is, incomputable, so you can really use it in practice. Neural networks are all the rage these days, and large language models. What they're doing is, when you're training them, you're minimizing log loss, right? Okay. So, if you have your data set, which is a long string, okay, you have this language model P, which is parameters by these weights, right? And you predict the next symbol given the history. Of course, they have a finite context, so it's not the whole history, but that's fine. Okay, and training means minimizing log loss. So you take the log loss with minus, right, and minimize over theta, and the argument gives you then, the optimal one. Of course, you do it with gradient descent. You may not get the global minimum and so on, but that's what you're doing. Okay. So, but this is the same as maximum likelihood, right? I mean, you put the minus away and without the log. So this is the same as the maximum over theta, p theta from x. Sorry. You sum here, of course, over all time steps. I mean, you train on the first token, and you train on all the tokens, right? Up to n. You pull the sum into the log, which gives you a product, and the product of the conditional distribution gives you the joint distribution. So that's the same as taking the likelihood function and maximizing this. Okay, so minimizing log loss in LLMs. So maybe I should have a heading here. Is the same as maximum likelihood estimation. Okay, and we know that, for simple model classes, of course, these model classes are not simple, but if the model class were simple, alt marks, that would converge to the two parameter, assuming, of course, that your true parameters in the model class, so that is the class, the LLM class, right? That the LLM can represent it. Okay. That is really, lots of assumptions here, lots of shortcuts very quick. Okay. So if you would do that, so you have some sequence, say, Bernoulli 1/3, you train your model on a Bernoulli 1/3 sequence, then you stop training, and then you use it for prediction. If everything goes well, it would then predict, Bernoulli 1/3, right? But this view is maybe not the most appropriate one, because these models are trained on a lot of data, right? And there's a chunk of maybe fair coin flips, and then there's a chunk which contains the digits of pi. So more plausibly, actually, our data set looks like x1 to n, and then we chop it up. So you have multiple data sets, and the first one is maybe, as I said, below half. The next one is a Wikipedia page, and so on. So that's more realistic. Okay. So how can we model this? So let's assume that so these correspond maybe to some parameters theta k, right? But let's assume let's assume that this k, don't talk about theta, yeah? This k is itself sampled from some prior distribution. Let's call it W of k or something like this, okay? So maybe I have to put a dot here, right? Some prior, okay? So you view the real world data as, okay, first I pick a website, and then I train on this website, right? And then I pick another website, and this website, one website could be pure noise, the other website is Wikipedia, the third one is a program, and so on. Okay, so that's a better view of the data. Okay, what does it mean? Sampling k, and okay, and these ones, these x1 to nk is sampled from the distribution, say nu k. Okay, so what does it mean? First sampling k,
so
and then
W is the weights of, like, you could think of these. I'm thinking of these cases like indexing different documents, right? And W is the weight of
I mean,
different documents.
maybe it would just be uniform distribution in this case. Yeah.
Okay. And then nu of K. Oh, I see. Nu of K is the language model of language within that document, essentially.
Yes, I mean, it could be, in this case, it could be deterministic, right? Just the content of this website, right? Or it could be sort of, if it's an agglomerate, if you take sort of K to index over, okay, here are all Wikipedia pages, here are all Twitter pages, here are all programs, right, then it would be sort of reader distribution. But if you find going more, it would be deterministic. It doesn't really matter at this level.
Okay, sure. So, okay. Yeah.
The point is, you sample K somehow, and then you sample X from new K. So that's an approximate model of where our data comes from. Okay. So what does it mean is, okay, what distribution do we get out? So we take the new K. Now, first we take the K, but we take it with probability WK. And then we sample our X from new K. So the probability of actually getting, if K is discrete, it's a sum. It's something like this. It's a mixture distribution, right? Yeah. So the whole worldwide web data is better represented as a mixture over different distributions, right?
Sure.
Okay. So that is our training. So the distribution or data is, roughly speaking, sampled from something like Xi, okay? Rather than a p theta. I mean, from a very abstract level, there's no difference. But that means if we train on this data, the language model, if it has the capacity to represent Xi, will then learn Xi, okay? And if we then use it for prediction, it will be a Xi predictor, okay?
Sure.
But Xi is a mixture. So that means, for instance, if we take the Bernoulli theta class, we give the model, we sample a Bernoulli 1/2 sequence trained, then we sample a Bernoulli 0.8 sequence, then we sample a Bernoulli 0.1 sequence, and we sample. What the language model should converge to, it should converge to the Bayesian mixture over this, which is Laplace rule.
That's it.
And it does. So we tested this, and it perfectly does it, okay? Which is pretty amazing.
I see. I mean, okay, that makes a lot of sense in the Bernoulli case. Just to make this more concrete, in the linguistic setting, this would be something like, okay, suppose for simplicity, you have two domains. You have children's stories and academic articles. And basically, as you sample more and more tokens, if it's really from a children's story, then the prediction should be more and more children's story-like. And if it's more of a scientific article, it should be more and more scientific article-like, right? That's just the linguistic way of reformulating what you just said in the Bernoulli case, right?
Exactly. And we tested it beyond Bernoulli. Yeah, we didn't test it for language because everything is muddled, but we used piecewise IID data, which is a little bit more difficult than IID, also works. Okay. Then we used this CTW distribution, this highly sophisticated distribution, which I introduced before. And the model also perfectly mimics the CTW distribution in context. This is pretty. So first it was even better than the CTW, which theoretically cannot be the case, but then we found some bugs, some inconsistency, how we train and how we do the inference. So we fixed the bugs, and then it was equal performance, but it was really funny. So this paper's out there, so people can read about it. And then we got ambitious. I mean, then we thought, okay, what we really would like to do is to predict the Solomonov's distribution, but it's incomputable. Let's assume we can sample from this distribution, train a large language model on data which is sampled from Solomonov's distribution, and if everything goes right, then the model would be able to, in context, emulate Solomonov's distribution, which is the perfect predictor for everything.
Okay, sure. Actually, just one thing. I'm trying to think what could have gone wrong, because why is this significant? And it sounds like to me what could have gone wrong is that the mixture does not update in the way you expect it. So it could have been rigidly 50-50 this domain or that domain, no matter how large the context is, right? And I mean,
that's a very specific way it could go wrong. But
that's one way it could go wrong. Yeah.
But I mean, the way it would technically go wrong is that transformers just don't have the capacity to represent these mixtures, right? The assumption
Sure.
always
That's
that
right.
the theta zero is in the class, and that a Bernoulli theta for a fixed theta is in the class is very plausible because it's just IID. The Laplace rule is in the class, counting the number of ones and counting zeros. This should be able to, but they are not so good at counting, and also the context is finite, but it still works, yeah. But these more complex classes, it is a priori not at all clear that the architecture of a transformer is rich enough to represent even this mixture distribution.
Oh, I see what you're saying.
Not to speak of that the training method gets you there.
Okay. Although language is a very complicated, I guess, in some sense, potentially unbounded or no fixed order Markov process, right? So it since it can represent language well, I don't know how it can represent other things, but okay. Anyways, just some off the cuff thoughts. Okay.
Anyway, so we got ambitious and thought, wow, that would be amazing, But of course, we cannot even sample from Solomonov's distribution. But we did, we looked at some tiny programming language where short programs already output some interesting strings, and you sample from it, then you train the language. And, we get some positive results. It's very hard to tell, is it great or is it just good, or is it's more than just random garbage. So it does something, and we are happy with the result. But for these smaller model classes up to the CTW and the PTW, it was perfect. And with the Solomonov, it also does something reasonable. So, maybe, this is a way to go to, basically, we don't need any data, right? So all this is artificial data. It's all trained on artificial data. And then the model does all the actual learning from the real data in context, which is at the moment very respectable anyway. People, extend the context to millions and try to push everything into the context. I'm not so sure whether this is really the way to go.
Maybe just to clarify, I think maybe one way to say what I was trying to, or a better way of saying what I was trying to say earlier is, so you, going back to the slide, you train your transformer on this data, and you want it to emulate the mixture distribution, which is this psi right here. And one way to evaluate how well it learned it is precisely to generate longer samples and see that the rate at which it converges to the true mu, it obeys the right properties, right?
Yeah, that would be one to evaluate, but in this case, we could also just, at least for the CTW and the Bernoulli, we could directly compare the distribution to the mixture because we have the mixture, right? The practical evaluation is always against the truth, of course, right?
Of course, yes.
But the scientific evaluation, we could just evaluate against the psi itself.
Oh, I see. Right. You could just compute the probabilities directly from the model outputs and compare it to the mu in this case. Yeah. Oh, fair enough.
Okay. So we're nearly done with the prediction part, but sort of as a bridge to the agent part, let's consider loss functions and sort of actions, but let's still call them predictions because there's a major difference between the agent case and the prediction case. But the loss function still sort of can fit in here. So loss functions. So the protocol is similar to before. We make a prediction. But let's call this prediction now YT. Okay. Then we observe XT. Okay. Then we suffer loss XT, YT. Okay. The important point is that we do not see XT before we do the prediction. Okay. And in general, I call it prediction, but this could be in any other space. So if XT is in X, YT could already be in a different space Y. And so, for instance, say you do weather forecasting, but you can say, if it's rainy, I take my umbrella, and if it's sunny, I take my sunglasses, something like this. So the prediction or action is actually taking umbrella or taking sunglasses. So they live in different spaces of different sizes even. So that's all already included. The important point is that your prediction or action, whatever you want to call it, does not influence the environment. Still not. Okay. So your action taking umbrella, or sunglasses doesn't affect the future weather. I mean, we know there's a butterfly effect, but we are assuming that there's one. Okay. So if you do this, then the best we can do is, so we have the loss we suffer, but we don't know xt. Okay. So let's just take the expectation over xt. So the history is fixed. With respect to, well, ideally the true distribution, but I mean, let's take some distribution, okay? So that's the expectation only over xt. And then we want to minimize this loss. T, okay? And let's call this the rho predictor, okay? So the rho predictor minimizes rho expected loss. Now it's standard setup, nothing special, okay? And
what's the intuition behind the argmin of the yt?
Well, E index. Let's take mu to be the true distribution of your world x, okay?
Okay.
Then this expression is the expected loss if I choose action yt. So if I take the umbrella, I suffer a certain expected loss. It could be rainy or sunny, but in expectation, right, maybe 70% done. Multiply this loss with, my loss for rain. It's my expected loss if I take the umbrella, and then I have an expected loss if I take my sunglasses. But I want to minimize my expected loss, of course, and that's the reason why I did the argument.
I see. Sorry. Yeah. So, okay. Yep.
Okay. So what is the real loss I suffer with this strategy? Well, the real loss is, whatever the outcome is, whatever the outcome is, but the outcome is, of course, uncertain. The true xt is sampled from my true environment distribution mu. Mu is always a true environment, okay? So this is my true expected loss if I use strategy yt rho. Okay.
So expectation with respect to S above, that's with respect to your own model of the sequences, not the true one?
Above, it was the expectation with respect to some rho, not specified at the moment.
Oh, okay. I see. Okay.
But this is not the true expected loss. True expected loss, I have to take the expectation with respect to the truth, right?
Sure. Okay.
I use the rho expected predictor, but evaluate it with respect to the truth, of course.
That's right. Yes. Okay? Yes.
So now I take also the expectation over the history. So I just take the expectation here. Now I sum over all time instances. Let's sum to n. I probably don't need really I can't use infinity. Okay.
So to use your weather analogy, the rho could be like how to best choose your weather prediction, say in the United States, and then maybe now you live in London, and then mu is the London distribution of weather, right? So sort of you could incur loss because of the mismatch, for example.
Yeah. For instance. Yeah.
Yes.
Okay.
Great.
So let's call it loss of. So loss of rho is the total loss, lifetime loss, expected loss with respect to the true distribution for the rho predictor. Okay. Obviously, by construction, if I would minimize with respect to the true distribution, that is the optimal thing to do, right? This is smaller than the loss of rho, right?
Yes.
So if I minimize with respect to the criterion, right, then of course this is better than doing anything else. Okay, that's fine. But again, as before, we do not know mu, so we have to do something else, right? And you could be a machine learner and learn mu somehow, or you're a Bayesian and you just replace the mu by a Bayesian mixture psi. Okay? So, loss mu is the best you could ever achieve if you know mu. And let's look. Okay. If we use Xi, so we minimize the Xi expected loss and compare these two losses. Okay. And now I have to do a little bit of a funny trick. I take the square root here and the square root here, because otherwise I can get a bound, but it's ugly. So I just don't compare the losses, but the square root of the losses. Okay, just different. It's called the Hellinger loss. Okay, and oh no, I don't need to take any square. Okay, and ask, well, if this is bounded by a constant, for instance, then I would know if the optimal mu loss is finite, then the optimal Xi loss is finite, which is great, right? Remember, it's over infinitely many steps. If the loss of mu sort of has a certain frequency, maybe 50% or something, then the Xi loss also has the same frequency, assuming there's a finite bound. And the amazing thing is there is a finite bound. This finite bound, as usual, is the ln w of mu to the -1 now with a square root.
Is there, how do I say?
And for the specific case of Solomonov's distribution, right?
Is this loss like, I'm surprised it should be even finite in the first place, right? So it's sort of like, if it's like, if you have for example, if your loss is 0, 1 accuracy, then this loss function will generically have an infinite sum over ones, right? Is there some discounting?
No, look, it's different. Assume you want to predict. Say, assume the weather is Bernoulli 0.7 or something like this. Okay, yeah, and
okay, sorry, keep going. Yep.
And you have a loss function, and you choose your umbrella, your sunglasses. Of course, you often get it wrong, right? So you will suffer a loss, right? Which okay, well, actually, so I need the n because that's infinity, right? So I need
exactly. That's the point I was trying to make. Yes.
I need up to n, and then this is n, and this is n. But then I can. But then I can take the limit n to infinity on the left-hand side.
Sorry,
not the n root, of course.
Yeah, okay, thank you.
N. N.
Yeah.
N. N. Yeah, I wasn't quite sure with that. I need this.
Essentially, this is like a regret bound, essentially, right?
Yes, except that there's a weird square root.
Yeah, sure, exactly. Yeah. Okay, you're right. Yeah.
But you can convert it over. But this is the best way to see it in the simplest way and the fastest way. That's a very, very neat bound. Okay, so that shows, I should have, this bound holds if the loss function is in 0, 1. So it must be a bounded loss function. Any bounded loss function, you can scale it, but if it's unbounded, it's more complicated.
Okay, so not cross entropy. Okay, yeah, sure, or something like that. Yeah.
So the nice thing is that Solomonov prediction is also optimal in this sense with respect to any loss function you care about, not just the square distance between the distributions or the log loss or something like this.
Yep.
Okay, now we are really done with this section.
Okay, no, this is great. This is great. Yeah, so just to maybe make one remark, because of the optimality that we discussed earlier, which is that if you have any computable measure, then you're going to assign less weight up to constants than the Solomonov weight, which is 2 to the minus Kolmogorov complexity. Then this upper bound becomes larger because of this log of a reciprocal, right? So in this sense, the Solomonov prior gives you the best convergence rate and also the optimal regret, right? Which is the minimal regret, right?
Yeah.
So this is amazing. Right. This is great. Yeah.
It is.
Okay.
So let's end with a nice, or maybe we can start the next section. Or you can cut it if you like.
Sure, of course.
So let's end or start with a nice quote of Marvin Minsky. when he was quite old, 2011, and he never worked on Kolmogorov complexity or Solomonov induction, but there was a panel discussion with him and Gregory Chaitin and some others, and it was 1.5 hours, and the last statement in this whole conversation by Marvin Minsky was, and I'm paraphrasing, I don't know exactly, but pretty much, Solomonov's theory is a beautiful theory about prediction. Everyone should know everything about this theory and spend the rest of their lives working on it.
Wow. Okay. Noted. So why don't we now start on part 2 of our outline? Let's just maybe quickly recap what we've done. Part 1 was called Universal Prediction, and we explain how, well, there's the Bayesian setup, which tells you how to do prediction once you update your priors to get posteriors that are now data informed, data revised. We introduced Kolmogorov complexity, so we could talk about the Solomonov mixture distribution or Solomonov prior, however you want to call it. And that gave us a prior that had optimal convergence properties, both with respect to prediction and loss. And then we also discuss some interesting model classes. But what we've left out is action planning, right? Because at the end of the day, intelligence requires interacting with the world. Those actions will influence the world. And so we want sort of the action version of this. And that's where the universal artificial intelligence comes in. And this is where your contribution comes in, right? So is that a fair summary of where we are?
Yes, I mean, my contributions, I mean, apart from Solomonov's original bound, everything else I told was also sort of a lot of my contributions. And there's much more I have done. There's this paper, a philosophical treatise of universal induction. There are so many other bounds and interesting insights you can have, right? Where, unfortunately, there's never time to get to this. But I mean, this paper in a lightweight form, and there's an older paper in a more heavyweight form, contains sort of a summary of all the other stuff related to Solomonov induction itself. Yeah, but the major contribution is indeed to the active agent case.
Yeah, I should say, of course, your books will be a proper monograph giving citations and references, so people who want to know more about the contributions can refer to that. But okay, great. So maybe should we just get started in section 2? We're pretty open-ended. I guess basically we want to adapt, kind of technically my sense is we've done a lot of the work. The planning part is sort of, at least at a high level, a modification of that, in that, okay, now you just add this action part, and you can talk about kind of the same theorems they carry over, and now it's a matter of reinterpreting it. Of course, there's many other downstream consequences of that, but at a high level, I think we've done most of the technical conceptual work, and now it's sort of shoehorning in the action part, and you can ask the same questions, right?
Yeah, you can ask the same questions, but you don't get the same answers.
Okay.
The active case is much more complicated and much more tricky. I mean, apart from the base optimal notion, which is sort of an optimal notion, which is, I would say, good by definition, or I mean, from the foundational derivation of probability in base, it's very difficult to come up with notions of optimality in the agent case, which are on the one hand strong enough to be convincing, but on the other hand weak enough so that real agents can actually satisfy them. So that even the right notion of optimality is still open, I would say. Unlike in the prediction case where you just use regret or redundancy and sort of, you don't have to compromise much there. Anyway, okay, let's start with the agents. And for a second, let us forget about Solomonov and all these kinds of stuff, but start very simple. Let's assume we know the world, right? What's happening, okay? So the setup is the following. I mean, it's a typical agent environment setup, and soon the rewards come in. I draw the picture a little bit different from the standard way because standard RL is usually MDP based, and that is too limiting for AGI agents, right? We want something, at least when we start, something which is general. That means general history based environments and policies. And so the picture I usually draw is you have an agent, and you have an environment, and they interact with each other. And And the agent as well as the environment, they can remember stuff arbitrarily long in the past. So let's sort of put this sort of on a tape. Yeah. So there's a sequence of perceptions. So E's are perceptions. That was the X before. The agent can have, okay? And once it has a perception, it can act somehow.
Is perception the same as observation?
No. You will see in a second.
Okay.
The agent then acts somehow, and it, this action can depend on the whole history of perceptions up to time step 3, and then the environment gets and can remember all the past actions of the agent if it wants to, and then produces a new percept. So that's the reason why it connects to E4. So that's the next time step. It produces a new percept, and then the cycle continues. So formally, what we have is we have an agent, which we call, the behavior of the agent is called a policy, right? Which takes, and here in this picture, it looks like that the agent only depends on the perceptions, but the agent can also remember its own actions. I don't need to sort of, because it produces the actions, rather because it knows its own actions. So the policy with a mapping of past actions and perceptions up to the star means sort of, like 1, 2, 3, 4, 5, and produces a new action. And the environment is also having access to the whole history of action and perceptions and the last action of the agent, and then comes with a new perception. And since the policy and the environment can be stochastic, I just write this as a wiggly arrow. Wiggly means it can be a stochastic mapping. I'm sort of across A, 2, 0, 1, like this. Okay. So, and this interaction produces an action observation or action perception sequence. So ET is sampled from nu of ET given, and now I use this glue notation A sometimes disappears here, A is less than T, and the last action of the agent, AE. So AE is sort of glued together. So it's action 1, perception 1, action 2, perception 2 up to T minus 1. And the actions are sampled from the policy, or the deterministic policy is just, deterministic output action given the action perception history, right? Okay, you start at T equal 1, there's no conditions, and you generate them sort of, based on the product.
So this is AE tuple, like all the pairs of AE up to less than T, right?
Yeah,
just to emphasize, so maybe just.
So the joint distribution, so we can do that. So if we take, we start at T equal 1, and the first thing is the agent's action. So it produces an action with a certain probability. So T is equal 1, so there's no history, it's just the first action. Then the environment reacts to this action. And then, T equal 2 starts, T equal 3 up to, say, T equals, assume the agent dies at times that M. So for simplicity, I just assume that the agent has a very long horizon M, say lives for 100 years and then dies, right? So, but you can also be infinite horizon, but then you need discounting for the rewards and so on. And infinities is always a little bit annoying. So I keep it simple here. So this is a joint distribution which generates the action perception sequence up to M, which we denote by nu pi. Okay? Maybe I should get this of E1 to M. So that's the probability of this action perception AE. Okay. AE1 to M. So that's the probability of the action perception sequence if if agent pi interacts with environment nu. So now we ask, what does the agent do, right? And we wanted to do well with respect to some criterion. And in reinforcement learning, you have a reward signal. So we split the perception into an observation and a reward. Yeah. So the perception is that observation reward pairs. Yeah.
Okay.
O2, R2, and so on. So when I write E, it's always the pair OR. Okay. And the goal of the agent should be to maximize its total reward over its lifetime up to M. But these rewards are stochastic, right? Definitely the environment. Either the environment is itself stochastic, or later we have a belief over the environments. So this reward sequence happens with a certain probability, right? And what's the probability? Well, the probability is nu pi, right? But the policy pi we want to choose, right? We only care about the stochasticity of the environment. So the probability of observing a certain perception sequence given a certain action sequence, actually, I come to that later. Let's keep it simple. So this produces this reward sequence, but with some certain probability. So let's take the expectation. So the expectation is with respect to the environment nu and with respect to the policy pi. Okay? And this expected reward sum is called the value of agent pi in environment nu.
Sorry, I think your R's and your nus look similar. That's an expectation of rewards. Is that right?
In the squares is R's. The index is a nu. Sorry. Okay,
yeah,
I'll try to be.
Your R's and nus. Say, all right.
Well, I think what they have. Anyway.
Okay. Anyways. Okay.
So that's the value of agent pi in environment nu. Okay. So if we know the true environment.
Okay. By the way, and are you absorbing the discount factor into the rewards then?
No discounting here because it dies at horizon M.
So, I see. Okay.
Yeah, I could do discounting, and then I can take the limit M to infinity, and all these versions exist, and they're also more useful. So, but I'm not doing that. And there's also, you don't want geometric discounting because for any gamma you choose corresponds to an effective horizon, which is 1 divided by 1 minus gamma. So if you choose gamma 0.99, it corresponds to an effective horizon 100. But there are problems which need larger horizon. If you choose gamma 0.999, it's horizon 1000. But there are problems which need higher horizon. But there are discount schemes which are not geometric, which generate agents with a growing horizon, for instance, proportional to the age of the agent. It makes a lot of sense, right? But I don't want to go into this.
Okay.
Okay. So if we know the true environment, then the agent's pi's true expected reward sum, so the true value is V pi mu. And well, we want to maximize this, right?
So mu is the true environment, and nu is the
nu is some environment, some arbitrary environment.
Got it. Okay. Yes.
Okay, let's call it rho so that it's easier to read. Yeah.
Check.
Okay, and this, let's call it pi star. Okay, but so that would be the optimal policy, right? If we knew in which line we are. Okay.
That's it.
Okay, but well, we don't know mu, so what do we do? Yeah. Okay, we learn mu. How do we learn mu as a Bayesian? What could we do?
Well, Bayesian updating.
Yeah, Bayesian updating, which means if in the predictive formulation, you just replace it by psi, the mixture distribution.
Sure. Yeah, exactly. And then as you make more observations, you'll get convergence.
Exactly. Okay. Yeah. So now let's define also pi xr Bayesian mixture. Well, the Bayesian mixture is pretty much obvious. I mean, everything is now conditioned on action. So, I mean, I could write it down, psi of x1 to m, so e1 to m, given actions a1 to m is equal to, well, nu E E1 to M given A1. So there's some subtlety. This is not the real conditional probability, but I use a double bar. So here is sort of, remember at the beginning I said there's a difference between conditioning and indexing. So that is actually indexing on A. And here it makes difference. Some people have spent a lot of time and figuring out what is going on here. I mean, in one sense, it's trivial. In another sense, it's really subtle. What I call them chronological semi-measures, say chronological probability distributions, which satisfy the causality constraints. But again, we don't have to go into it. It's in some sense, it is obvious. Okay, so now this pi star, that is what we want, pi star mu. But we cannot have it because we don't know mu. So we use this policy pi star psi, okay, which I call AI psi. It's not the IXI model yet, but we are close, okay? So, and now we want to compare the performance of this Bayesian agent to the agent which knows the world, okay? So how can we do that? Well, we look at the value, but this psi value is just sort of a tool for creating a policy. This has no meaning, right? I mean, not direct. What we really receive is the mu value, okay? So, but we act with a psi optimal policy, okay? So we ask, what is the true mu expected reward sum if we act with a psi policy? And we compare this to the optimal mu agent, okay? This optimal agent, of course, has smaller value than any other policy by construction because it's just the argmin. But what is this relation between the base agent and the optimal informed agent? And well, in the predictive setting, we proved this loss bound, so Solonov bound, and so on. And in the active setting, under certain extra conditions, you can also prove asymptotically that they converge to each other on average. You can prove so-called self-optimizing results. You can prove asymptotic optimality results. There's weak optimality, strong optimality, optimality in Cesaro sense. There's lots of different optimality notions, but they all come with conditions under which this holds, so they're not condition-free. And
conditions on conditions on
let's
what?
not go into this.
But conditions on what? The class of
conditions
environments?
on the class M. Yes, conditions on the class.
Okay.
Yes.
By the way, I think you meant lower bound. We're trying to maximize reward here, right? Argmax.
Oh yes, yeah. So this is approximately the same in a certain sense under certain conditions. Conditions on M. I mean, for instance, this framework is general enough that if you choose a class of environments M, which do not depend on the action, so if I cut this arrow here from the action tape to the environment, so in the diagram, so if the nu respects this, so it does not depend on the action, so here I may have made an error if it does not depend on the actions, then we are back in the passive prediction setting. And for instance, for this class of models, right, we get the Solomonov bound back. Yeah. But we get also bound beyond this class, of course, otherwise it would be bored. Okay. So finally, that is nice, but we have to choose a class. And from an AGI perspective, right, we want the class to be, I mean, from a technical perspective, we want it to be as small as possible to deal with it practically. But from an AGI perspective, we want to big enough so the true world is in the class. And I mean, if you look at physical theories, standard model, generativity, and whatever, they're all sort of computable theories. I mean, very hard to compute, but they are computable. So again, if you take the class of computable probability distributions, you should be pretty safe that the true world is in the class. Yeah. So again, we choose M to be mu, which is all computable. In this case, lower semi-computable chronological semi-measures, if you want to be precise, but roughly speaking, all computable probability. And as before, we choose 2 to the minus the Kolmogorov complexity of nu. Then you get a psi, which is psi u, and this is called the RXC model. Okay? And now if you think even intuitively about what this model does, it combines universal sequence prediction, which we have shown to be optimal, with optimal decision making in known environments when it's also optimal, and combining this in these 2 ways by just plugging Solomonov into the sequential decision theory framework sounds like an optimal decision maker in arbitrary unknown worlds. And if you parse this sentence, this feels like AGI. And you can also define an intelligence measure out of this. So you can regard V psi pi, that is the performance of policy pi averaged over all environment in the class with a certain prior. And you can call this, for instance, the intelligence of an agent pi. And Jane Legg, my first PhD student and co-founder of DeepMind, wrote a whole PhD thesis just about this intelligence measure.
So pi is a policy, psi is this Kolmogorov, the Solomonov mixture prior, right? And you're calling this value function the intelligence?
Yes, the intelligence of agent pi, so epsilon of pi. Because, this is, we can write it out explicitly by linearity. This is just the sum over all values in all environments over the class times.
Oh, I see. It's sort of like measuring its fitness with respect to general environments. Is that how to interpret it?
Yeah.
Okay.
Yes. So it measures the average fitness over these environments, averaged with a sort of outcomes prior.
I see. Let's take this down to earth a little bit, because we're working in the space, the countable space of all computable programs. In practice, right, we never do have this infinite space where we have to juggle all these quantities. In practice, there is some finite subset of discourse, of consideration. And I'm wondering to what extent, if you choose a large enough finite set, sort of this becomes, say, applicable, tractable, meaningful, right?
Yeah, but that is probably a little bit too naive. This finite set needs to be really large, right? So assume you can describe our universe in 100 bits, right? 100 bits is not very much, right? So, but assume you can describe in 100 bits, right? There are 2 to the power of 100 programs of up to 100 bits, right? So that is already a class of size 2 to the power of 100. It doesn't really help you. So unless you can do the mixture more efficiently than naively, like in the CDW case.
I see. Yeah. So basically, as soon as
it becomes computable, but practically not.
That's right. Very large finite numbers are basically out of reach very quickly in this business.
Yeah. Anyway, so that's all good. Let me briefly, that looks very abstract. Let me give you another formulation of this agent, which is much easier to grasp what is actually going on. Here we're doing an argmax over policies, and policies are functions from high-dimensional spaces. There's a different way to writing this down. Avoiding all base and mixture and all this kind of stuff. Let's first again start with the true distribution, mu of E1 to M given action sequence. And again, this is not really the conditional distribution. Okay. So that's just the perception sequence, assuming that a certain action sequence is done. Okay. So M is where the agent dies. We don't care about the last perception. That just what a second. The goal is, of course, to maximize reward sum. Okay. But the last perception we don't care about. So let's just take it out. And what that means is that we just take the expectation over the last perception. So now we have the last action. And then the world ends, right? Or the agent ends. So what do we want to do? Well, we want the action to maximize reward. So we take the action, which maximizes this reward sum. Okay, so that's in the last. So we're going from back, right, from the last day or last second of the agent, and so now how did we get there? Well, the environment produced a perception EM minus 1, and before the agent receives the perception, we don't know it. So let's take the expectation that this is E minus 1. Okay, and now we take the action at time m minus 1, which maximizes the expected future reward. So that
I mean, you're for those, I mean, you're basically unrolling the Bellman optimality condition, right?
Yes. Yeah.
Okay.
And the Bellman equations are really only useful if you have a Markov process, right? Because then you really have this self-consistency. But because it's history-based, I mean, you can write it down in a Bellman form, but it's it's not really recursive, because at every recursion step, you have a different length history. So you don't really gain anything.
Okay, yeah, if this were the MDP, but you're basically unrolling the tree,
correct.
right? And you're just working backwards. Yeah.
Yeah. Okay.
Okay.
So, and then of course we go up to assume we are currently at time step k. So we sum over the ek and we take the maximum at time step k, and then the optimal action is just the argmax. Okay. So, and you can write it down in a tree, right? If you look at the tree representation.
Right. I mean, basically, you decide. Right. Once you decide what the optimal move is at a node, then you can analyze the optimal move from the parent, because the parent, you have the reward for each action, and then the value of all the of the child, which encapsulates all the decisions below it, and so you just kind of recursively work your way up, right?
Exactly. And so if it were a classical minimax game, right, you would maximize your value when you have actions, and the environment would minimize the actions, so then you would have a minimax tree. Okay. But here the environment is not necessarily adversarial, it's stochastic. So instead of a minimax tree, you have an expectimax tree.
Yeah,
so
that's right.
The reason
That's right.
why you have these expectations here.
Right.
So these sums are the expectation.
Yeah.
Okay. So that is the expectimax max tree. Okay, so far so good. This is if we know the environment. And by the way, we can specify, assume we play chess, so we could define an environment mu, which is in this case deterministic, which is adversarial, which means it would only put probability on one particular, from the environment's perspective, action, from the agent's perspective, observation, namely the optimal action. Then all these sums would collapse to picking out the minimizing element, and the expectimax would reduce to minimax. So if mu is the chess environment with an optimal opponent, then this would reduce to minimax. So I just want to say it includes also minimax adversarial.
Right, because I think what you're saying is that if you play against the strongest possible opponent, there's no margin for error. So they're always going to choose the thing which minimizes your reward, which maximizes the adversary's reward. So everything concentrates on the best moves, and because that's right. Mm-hmm.
Okay, so far so good, but that's with respect to the true environment, right? What if we don't know the truth? Okay, now the pattern repeats. What do? We replace the mu with psi,
the mixture.
Right?
Yeah.
So I could just write psi here, and we would be done. But let's be a little bit more explicit. So remember, in the prediction case, there were two formulations of this psi. One was in terms of Bayesian mixtures, and the other one was just piping random noise through a universal Turing machine, which was, much easier in a certain sense. So we can do the same here. Nothing much changes. So we look for programs P, which output perceptions E1 to M. But now, need some space. We have actions as conditions, right? So the universal Turing machine also has the actions available, okay? And we look for a program which, given the actions of the agent, and produces the observation sequence, so explains the observation sequence relative to what the agent has done, okay? So, and we weigh each program by its probability. And, the probability of a program should be 1/2 to the number of bits. So we weigh each program by 2 to the minus L of P. And there are many programs which output this observation sequence. So we sum over them.
Yeah.
So in this formulation, you look for all deterministic world models, P, which are consistent with the observations, E1 to M. But it also depends what the action does, right? If I look left, then I see the perception is different than if I look right. So everything is dependent on the actions. That's the reason why the action is also a function of you.
And sorry, was there a reason we went back to the deterministic case? That I assume this all works in the indeterministic.
Because to write it down explicitly, I mean, can write psi, and then we can look up psi and so on. But now what we have here is, if I circle this here, apart from the definition of a universal Turing machine, which is sort of, not trivial, right? Everything is completely explicitly in here. There's nothing, there's an action space size and observation space size, which you have to specify. But otherwise, everything is here written down explicitly. Nothing is hidden. I mean, that's the only reason to write it out like this. I mean, how do you enumerate all computable probability distributions? Yes, you can enumerate all functions, and then you can, top these functions towards the problem. So, I mean, there's a long process to really get to this Bayesian mixture distribution. But here, this is trivial, right? So you just write it down in, 20 characters. That's the only reason. It's equivalent. I can just write psi.
Okay, sure. Sure.
Okay, so that's this IXE agent. And I guess we can move on from this. I would like to talk about some variations of this model, which has advantages and disadvantages. So given that it's very hard to prove convergence results, alternatives have been developed. So let's go back to the original formulation where we had where we took let's maybe this formulation. We had the psi value, one representation what we represent as a new value times its prior, and then sum over all new in the class. So that was the psi value, and then we argmaxed it to get the optimal policy. Okay, so here we look for the performance to maximize the performance averaged over the environment.
That's it.
Okay. What we could also try to do, we could do a minimax instead of this. We could do the minimum over all new, maybe still weighted, right? Over new. And then argmax it.
The first line is just linearity of expectation, right?
The first line is linearity of expectations, yes.
Yep, okay.
So if we replace the sum by a minimum with or without this weight, that would be trying to perform best in the worst possible worlds, right? We look for the nu, which gives me minimal value, and I want to perform well in this. That would be sort of a minimax strategy.
Okay.
Interestingly, if you have prediction problems, that can work under certain circumstances well, usually of finite classes or compact classes and so on. But for the active agent case, that is actually a bad idea. Very interestingly, if you replace the minimum by a maximum, so it's a maximax principle. So you look for the best possible world and you want to act well there. You can show that at least for finite classes, you get an asymptotically optimal agent. And then you can extend it to countable classes with some tricks of making the class growing. You can extend it to compact classes. I mean, compact classes always you fill it with finite degree epsilon balls. Then you can extend it to separable classes, this result. So anyway,
so this is, I mean, this is saying like you should be, under these assumptions, you should be an optimist, not a pessimist, right? You act as though the world is in your favor. And if you try to optimize that situation, you'll do the best, versus the other way around, where I'm going to act in a way such that I assume the world is most against my favor, right?
Yes, and you can explain it in two ways. So we know as soon as we go to the active setting, we need exploration. And being optimistic encourages exploration. So if there is an environment where we, look, this is all still Bayesian, so we don't know much about it. So if we believe it could be good, right, then we try it. And either it is good, then it was a good action, or it's not good, then we have learned a lesson.
Yes.
And then based on the posterior, it will go down. So the optimism gives you exploration.
Okay. Was there something else?
So this is the optimistic agent. The optimistic.
Yes. You said there were two things, right? Optimism is exploration. Was there something else?
So it encourages exploration, and and also, I mean, if you are optimistic and then you act, which I said, either you were right, then everything is good, or you were not right, then you learned a lesson. And this lesson sort of useful.
This is a bit of a philosophical tangent, but I think where this makes a sharp contrast with reality is that two things. One, we as mortal human beings, positive and negative rewards are highly asymmetric, right? Death is like a negative infinite reward, and in some sense, positive reward is bounded because there's only so much, money or diminishing returns, right? And then in practice, people do have a concave reward utility function for precisely that reason, right? We're much more risk averse, and so we're usually more pessimistic in some sense than optimistic. Anyways, maybe this is too much of a philosophical tangent, but that's just something that. Why are we more optimistic? Because I think our situation differs from the assumptions of whatever this agent is, by what I just said.
The assumptions are here that the rewards are bounded in the interval 0-1, or at least sort of in a bounded interval. Mm-hmm. In my old book, I have a whole section about how to deal with concave loss functions and how to reduce this and so on. Yeah, we could bet a whole podcast.
Sure, okay.
But let's not do that.
Of course.
So, and also, this is not naive optimism. You have to update with the posterior, right? It is a
realist.
A realistic optimism. Yeah.
Yes, that's right.
Okay. Because you take the feedback into account, right? You eliminate the posterior, the environment, which made it consistent with what you were hoping for.
That's right. Yeah, that's right.
Okay. In a very tiny setting, the UCB algorithm, upper confidence bound for bandit problems, right? That's a similar. It's similar, right? You're optimistic with the arms, and either you were right or not. Then you learn something, and that you still respect your posterior belief. In the environments. Okay, so that was the optimistic agent. Another agent is Thompson sampling agent, for which that is one agent for which you can actually prove without any real restrictions asymptotic optimality, at least for some form of asymptotic optimality. And what you will there is, so now, I said I try to avoid the posterior and be predictive, but here we go back to the posterior. So we look at the posterior probability of an environment nu given the action observation sequence, up to a certain, time n or so. Okay. And we sample nu from this posterior distribution. So just, at the beginning, it's a very broad distribution, and then it's biased towards simple distributions. And then we learn more and more, and then it concentrates more and more on the true distribution. So after a while, right, we would sample with high probability the true distribution, but with lower probability other distributions. Okay. And what do we do with this distribution? Well, we choose the policy which maximizes the sampled distribution. Okay. So rather than before, this IXC agent, IXC or IXC, depending on what distribution you used, was pi psi star maximized with respect to the mixer distribution. Now we just sampled one distribution from the posterior and then maximize it with respect to this. So this is Thompson sampling. And for the MDP set, for the bandit setting, has been shown to perform as well as these UCB algorithms. Again, it's all rough and they're bounds, sometimes this, blah, 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 but, it's all rough statements. And,
XC is a special case of AI psi where you chose the psi according to that formula you just wrote, right, in terms of complexity. Okay. And then Thompson sampling, I'm a little, what's the difference? Or what's going on here?
Forget about the, IXC, just talk about AI psi, okay? So AI psi follows the policy P psi star, okay? In the previous slide, it was in the previous slide. If you go to the previous slide, I defined P psi star, okay?
That's it.
If you write down the actions which are actually performed by P psi star, then this is what you see in the current slide 9, which is the AKI in this big formula which is circled around. So it's the same thing. One is explicitly written out and the other one was implicit. Okay, so that's the AI psi agent. Okay. So now what we're doing is we are not using psi at all. We are sampling from the posterior. What is the posterior plausibility of an environment? And we sample with respect to this probability distribution. So plausible environments will be sampled with high probability, implausible environments will be sampled with low probability, okay? We sample one of these environments, and then we pretend we are in this environment. We ask, what is the optimal policy?
Yep.
And we choose this, and in the bandit setting, you just choose it once, and then at every time step, you sample again. In the agent setting, or even in the MP setting, you have to do this, follow this policy, follow for, say, k time steps. Steps,
I see.
Where k is the effective horizon. And so if you have geometric discount of 0.99, that would be you follow it 100 like this. And then you sample a new policy.
Sorry, so we've been talking about finite time step in this case. So is k equal to m?
No. K is equal to k.
Sorry, so what is the effective horizon in the case where you only have a finite lifetime?
The effective horizon is if you okay, so if you have no discounting, there's no effective horizon, yeah? So this is the discounted setting where we have here gamma 1.
Yeah.
And then
I thought we were in the finite lifetime setting, and then k is m.
Yeah.
Okay.
No, here you have to, you can still have finite lifetime, but that's not important. The important thing that you have discounting, and then the effective horizon is when these discount gammas are so small that they only contribute an epsilon, you can just cut them off.
Okay. Well, wait, so in the finite lifetime setting, how many steps do you run?
It doesn't work in the finite lifetime setting.
Oh, okay.
Yeah.
Okay.
You need to discount the setting.
I see. Okay.
So the effective horizon, if you have geometric discounting with 1 divided by 1 minus gamma, for instance.
I see. So this is kind of like how to say, the UCB bound for explore and exploit is kind of a explore and exploit along the axis of simulation, where different simulations, different selections. Here, you kind of do explore exploit in a temporal sense. You're saying I'm going to exploit for a bit with respect to new for k-steps, and then I'm going to I don't know if that's the right way to say it, but resample, I don't know, that's I guess that's maybe re-exploration, sort of like, right? So you could think of like a temporal version of explore and exploit. Exploit for a while, explore. Sort of, yeah. If you accidentally sample a distribution which is close to the truth, then you would exploit. And if you sample a distribution which is, low probability, but you happen to be sampled it, then it would be like an exploration, yes. Yeah, okay.
Okay, so that's the Thompson sampling agent. Let me give you one or two more.
Sorry, what's the significance of this? So basically, if you follow this,
you can prove asymptotic optimality for this one without any condition for the cloud.
Listen. I see. Well, you're okay. The whole point of this is there are ways of getting optimality without having to go to the XE route, essentially.
Yes.
Or actually.
I mean, it's very close. I mean, Thompson sampling is very close to Bayesian, but it's just slightly different.
See. Okay. Let's keep going.
Okay. So. So some people ask where do these rewards come from, and there could be various sources, right? I mean, either you have again, very brief. Say you have a household robot, comes out of the box, not trained exactly, what to do, and you just give it a carrot and stick, and it learns sort of what you like to do, what you like it to do, and then behaves appropriately. Okay, that would be one source of the reward signal. You could say send robots to foreign planets for finding life or collecting rocks or whatever, then the reward function would be hard-coded to, seeing certain images in the camera and so on. But what is if you want to design an agent which is generally intelligent, but somewhat independent of us, doesn't have a fixed goal, right? And doesn't require sort of our carrot and stick. And Laurent also, he thought about an information gathering agent. So it's sort of the optimal scientist or the most curious agent, which cares about learning about the world. So what he does is he says, okay, let's look at the reward. And the posterior is already here. We have a certain posterior distribution at time, say, t. Okay. And we compare this to the posterior distribution one time step earlier. Okay. And if the posterior doesn't change, then you haven't learned anything about the environment, right? You're still sort of, your uncertainty and probabilities, you assign to each environment, is still the same. So you haven't learned anything. Okay. So if you flip this around, we can say, okay, if it has changed, then we must have learned something, right? So he takes the logarithm and then the expectation, which is just the KL divergence between the posterior at t and at t minus 1. So this is the expectation with respect to the posterior. I mean, I can write it down if you want to. And then plugs the reward to this and calls it information gain. So this is, if I write it down, is W of nu AE 1 to T8, call it AE, ln W nu AE 1 to T divided by E less than T. So this KL divergence measures the change in posterior, and the more it changes, the more sort of the data has given you some information. And it just plugs this reward into the ICT model. And now we don't need to reward the agent anymore. But it also doesn't necessarily do what you want anymore, right? So the agent is now maximally curious to learn about what is the true environment in the fastest possible way. It's also safe from noise. So there was a first version, the knowledge-seeking agent, which sort of would have glued his eyes to a random screen because there's lots of entropy on a random screen. But this KL version solves it, so it only looks for real information.
So I'm a little. So there are the. Can you just start again? What is the significance of this? You're defining a new set of rewards and trying to optimize those rewards.
Well, the significance of this is that you don't have to provide rewards anymore. You don't have to provide rewards anymore. If you have an RL agent, where do the rewards come from? Where do they come from?
The environment.
Yeah. Right? Well, no, the environment is pixels or bits. What's the reward? You have to somehow specify which particular pixels on the screen or particular input corresponds to a reward. So
Is it-
somebody has to do that, right?
Is it?
Or you have a particular channel, and then the human gives the reward. So either you specify a reward function, then the agent just performs this particular task, or you constantly need the human in the loop, right?
Sure.
And what this does, it sort of specifies a reward function, but not one for a particular problem like playing chess, finding rocks on Mars, but to the problem of learn the true distribution.
Sure. Okay.
So maybe I skipped the last one, which I wanted to talk about. This IXE has this expectimax tree, which is expensive to compute. We also have the problem of computing Solomonov's distribution, but this is also an expensive part. And as you mentioned, there is a version divided down as Bellman equations, and then you don't meet this explicit expectimax. And there's a version of IXE, which is called self-IXE, which does that in a way and exploits sort of this structure. Let's phrase it that way. So that's called self-IXE, but let's just skip this self-IXE. Just search for it.
Okay, so to summarize, we took the ideas from part 1 about universal prediction, added in action, and the optimality conditions now become optimality conditions on things like regret and learning the environment. What you just outlined here were sort of, sorry, let me start before I jump to that. And you could even furthermore write an explicit formula for what IXE is. These variants that you wrote down were sort of different ways of trying to learn the environment by using other sort of strategies, let's say.
The learning of the environment was the same. The learning is always our base rule.
Okay.
But how to choose the actions was a little bit different. So the IXE chooses the base optimal action, the Thompson sampling chooses as well the Thompson sampling action, and then the knowledge-seeking agent sort of is exactly IXE, but chooses a reward function for you.
They're different. Yeah, I guess these are like kind of different policy learning methods, essentially. Is that a way of phrasing it?
Yes, Thompson sampling and IXE sort of is different ways of follows different. You have to distinguish between updating the push theory belief and what you do with this belief, right? How to act according to the belief, right?
Sure.
And so Thompson sampling and IXE are sort of different choices, and the knowledge-seeking agent solves a different problem, namely where do the rewards come from, and self-IXE tries to avoid the expectimax then.
Okay. Anyways, okay. So I think let's just leave it at that as the summary. So I guess we have time, some time maybe just to say just a few odd things here and there as we choose. I know you wanted to talk about the grade of truth problem. Maybe that's just one last thing we could put in. Maybe close with some philosophical discussions. We already had a few, but maybe anything that you'd like to. Kind of like final thoughts about the subject, essentially.
Okay, that's true. That's the multi-agent setting. Yes. So far, we have only considered one agent, but since the framework was so general that the environment could be anything, there could be, of course, other agents too. Yeah, but there is more to say than this. Okay, so let's first draw a picture, but I don't need to say too much of it. It's extremely sophisticated. The final result, what I want to present, the grain of truth problem was a problem which was open for 25 years, and then some of my students solved this. So you have now multiple agents, which each have their own policy. So they assume you have k agents, and the policy is pi 1 up to pi k, and they act with an environment now. So there's an index up there, so the agent 1 acts with AT1 at time t, and then perceives ET1 up to the last agent, so APK, and perception is ETK. So pretty natural, and of course it also goes in cycles. Okay. So what we could do is we could just look at the first agent and regard all this here, right, as an environment, right? This first agent, it acts and it perceives, and that this environment itself sort of consists of k minus 1 extra agents. We can ignore that to some extent, right? So let's call this class M.
By the way, are the agents always acting in succession, cyclic order always, or is that an irrelevant detail?
That's irrelevant for
Okay.
our discussion. Yeah,
Okay,
you can.
okay.
Yeah. Okay.
Okay.
I mean, technically, it becomes important, but for here, it doesn't matter. They
Okay.
act in parallel. Okay. Like in game theory, they have parallel actions, so on. But let's not go into this.
Okay.
So let's start. I started a little bit different. Before we looked at, I never specified a policy class because we just looked at all policies and then the best among all policies. So let's start with some policy class pi. Okay. Some potentially restricted class. Okay. And let's also assume that all these agents, have some policy in the policy class, not necessarily the same policy. Okay. And so once we have given the policy class and assume there's also an environment class sigma, but let's assume there's just one environment, doesn't really matter, right? There's also a class of environment sigma. We can construct then by, gluing these k minus 1 agents to this environment sigma and can create a traditional one agent environment out of it. Okay. And we do that for all possible combinations of policies in this policy class. And this generates a class, let's call this M capital pi. Maybe I should make a double bar so you see that's a capital pi. So that's this class M pi. Okay, so here we start with policies and create our single agent environment class M pi. Now we have M pi. The next thing is we construct our psi, the base mixture over this class as before, and now it is called psi, again it's invisible, M index pi. Okay, gets lots of indices. Okay. Now we have the base mixture distribution. The next thing we want to construct the optimal policy with respect to this base mixture, like the IXI model. Okay.
So just to get this straight, so you're trying to reduce this multi-agent formalism to the previous formalism where there was a single agent. So it almost sounds like to do that, you need agent 1 to act alternatingly with the other agents, right? So it's sort of like action and percepts, right? Is that an assumption?
The action and the perception is alternating, but all the actions are parallel.
Okay.
Anyway, let's not go into it. I can spend at least 50 hours on it if you want.
Okay, sure, okay. So let's continue. Okay. Yeah.
So now we look at the value of a policy. So of policy pi 1, I should call it, right? In this Bayesian mixture over this class we have just constructed. Okay. And what we want is, we want the optimal agents. So we take the argmax, and this is our pi 1 star.
So hold on, let's see. Let me think about this. I see. So M pi is the universe of policies we're going to consider. The C is the whatever. I know, what do you call it now? The Solomonov mixture, the AI-XC mixture. What's the name of the
base mixture? Just call it base mixture.
I should, but you are using it's any base mixture. But I thought you were using
at the moment I'm not using any specific Solomonov class or Solomonov.
Oh, I see. It's any base mixture. Okay, sorry. Okay, C is a general base mixture. Okay, that's what I was trying to understand. Okay, I see. Okay, please continue. Yeah.
Yeah. So psi index M always means the mixture with respect to the class M, whatever M is.
Yeah. Yeah. Right. I see. I see. M is the set and also the weights. Then I guess.
Yeah.
Okay. Yeah. Okay.
Okay. So we go from a class of policies to a class for a single agent environment. then we construct the base mixture, and then we construct the optimal policy with respect to this base mixture. Okay? So now, so far, all good. But now comes the real question. You know, we started with a class of policies, and via this loop, we constructed a new policy, pi1 star. So is this policy actually in the class or not? If it is not in the class, then it would mean that if we want these agents to be base optimal agents, then they are not in the class. But we started out with a class assuming that these policies are in the class, so we have a problem. So what we need is, we need pi1 star to be in the class pi itself.
Sorry, what is the obstacle? Because if you're considering the class of all whatever computable, semi-computable, blah blah blah, how could it not be? If you want a smaller class, is that what it is?
Well, if you start with a class of semi-computable distributions, then the psi is also semi-computable, but the policy pi psi is not lower semi-computable anymore. It is only limit computable. So it is one step further removed from computability.
I see. I see. In the previous setup with that was not multi-agent, I guess we didn't care where pi star lived. Now we do?
Exactly.
Okay.
Yeah. Okay. So that is called the grain of truth problem. Grain of truth. And the question is,
sorry, can you explain the naming of that?
I guess it comes from you want the true environment in the class, but it needs to be. It can be a very big class, and just one environment needs to be in there. And I think this is the grain of truth.
Okay. Sorry, please continue.
Yeah. So that was by Carly and Vempala, 1993 or so. So they formulated this problem, and maybe in this paper or in another paper, they or somebody constructed a tiny, super boring class where this grain of truth is true. I mean, it's more or less sort of an environment where you have a fixed action and then you die or something like this. I can't remember. I mean, it's not AGI. It's not even a banded problems. Nobody else could ever find any class, non-trivial class, where this grain of truth holds. And so that was this big open problem. And one of my students, Jan Leike, and some Miri guys actually before that, they found a class which is relatively, so the Miri guys constructed a class which it was not even sure whether the distributions in this class are in the arithmetic hierarchy. So this is something, I mean, really crazy. I mean, sort of again, just leave it like that. But Jan Leike then showed it that it's actually in delta 2, so it's limit computable, which is sort of the realm where Solomonov works anyway. So this class is not the class of lower semi-computable semi-distributions, but it's a class of all reflective oracle computable measures. And this construction is hell. Okay, let's not go into this. So we have, as a result, we have a class M, which contains all computable distribution, such that pi1 star is in pi. So contains a grain of truth. So the important thing is it contains the computable ones, which we want. And another important thing is not too big. It is at least a subset of delta to 0. It's not so crazy, which is really great because the reason why we care about to be this put in the class, that means the condition that psi is in the class is now satisfied. Yes. So the psi is itself in the model class, or the pi psi more precisely in the model class itself. Therefore, the conditions which you usually need for most of the Bayesian theorems. Most of the Bayesian theorems, if the true class is in the model, then good things will happen, right? And so this condition is now satisfied, and we can apply the previous theorems, and especially the one for the Thompson sampling agent. If we now do Thompson sampling in this multi-agent setting, we get an asymptotically optimal agent, which in this case means they converge to Nash equilibria in this ultra general, model class, which is I mean, from a theoretical perspective, it's a highlight of also the book. Then this result.
Should. Okay, wow. I think there's a lot to unpack here, but I think, at this point, only the experts are here. I think we could end with just two more things. I did say philosophical discussions, but maybe another important topic, maybe if you could just say a little bit about it, are computable approximations, because everything we've done now is sort of very abstract, and maybe, how would you modify this for real life?
Yeah, so actually it's sort of, I mean, to the extent that we have done it, it is easy to explain. So the first approximation we did is we just used for M the class of Markov environments. Actually, K-order Markov environments. Was it K-order?
Let's see.
Yes, I think K-order Markov environments. And for the K-order Markov environments, you can easily, I mean, the mixture over the parameters theta gives you, KT estimators. And then we used only binary actions, the observation spaces. And then the expectimax, if it's binary tree, you can roll it out to get 8, which means 16, 2 to the 16, sort of these days, sort of much more. And then we considered these small 2x2 matrix games like Prisoner's Dilemma, tit for tat, playing against trivial strategies, random strategies, against tit for tat. Sorry, there are games like Prisoner's Dilemma and Matching Pennies and Battle of the Sexes and Stag Hunt and the Chicken and so on. So there are 5 sort of standard games, and did some experiments, and the outcome was more or less like expected. I mean, these are now approximations. So if you play one stronger approximation against the weaker one, the stronger one wins. Sometimes they cooperate against sufficiently simple strategies like tit for tat. If it's too complicated, they don't cooperate. So more or less, sort of, it worked as expected. Next, more complicated approximation was then using the CTW. Remember?
Sorry, let's pause here. Sorry. Yeah. So now the ICSI setup worked for general computable environments. A computable approximation is when you say, sorry. Let's back up. There's the true environment, and then there's the class of environments you're going to use to approximate the true environment. And mu might not be in M. Of course, that's going to be most of real life, right? And so you're seeing how well can you do in this sort of misspecified setting, right?
Yes. I mean, if for instance, we let IXE play against tit for tat. Tit for tat is one Markov strategy, which is in the class, right? Then the theory should hold. But if we play against, a more complicated environment, especially if we play against itself, right? Then we are outside of the class, theory breaks down, and we have to just see empirically what happens.
Although, let me try to think if, what I want to say is, I see. You only have a binary alphabet or some fixed alphabet. Okay, I was going to say I guess
binary, very small alphabet.
Yeah,
because they
Yeah. Otherwise, if you allowed unbounded alphabet, then I guess you could include board games where you have a very large state space of possible boards. But obviously with binary, you're not in that situation.
Yeah.
Okay. Anyways, yep.
Okay, so that was the first very simple approximation. Then the MC-IXE CTW, there what we did there is we used this CTW distribution, right, which is much more powerful, but still very fast to compute. But now for larger either observation action sequences or for non-binary, you cannot just do the expected max brute force. But there's an algorithm called Monte Carlo tree search, which we just adapted to our case. And we deployed it to, which asymptotically for enough samples converges still to the exact expected max. But of course, I mean, in practice, you're never close. But, it's nice to have an algorithm which at least, is an anytime algorithm, if you run it long enough, sort of you get to the truth. So it still has, also this theoretical guarantees in these certain limits. And we applied it to a lot of toy problems like grid worlds and the most sophisticated, a very trivial form of poker called cool poker. And then we ran it on Pac-Man. Well, we call it POC-Man, partial observable Pac-Man. And for all the toy worlds, including cool poker, this approximation learned to play optimally, asymptotically. And for Pac-Man, we also saw performance improvements, but I mean, of course, it didn't converge to optimal. So that was a more sophisticated approximation.
For these situations, what's the observation is whatever, like in Pac-Man, it's the screen, right? There's some
that would
n
be
by n
Pac-Man, but we do POC-Man, where the agent only observed in the 4 directions. I can't remember exactly anymore whether it was up until a wall or up until some object or ghost or something was there, and then the distance or so, or maybe just one cell. So it was from a first person's perspective what the agent can see.
Sure.
Which made the observation space smaller, so it was more easier to handle in this case.
Sure.
I remember that was way before the Atari paper from
I see.
DeepMind. And by the way, this approximation was by Joel Vaness, who then also worked on the Atari problem. So it evolved from MCI playing Pac-Man toward the Atari suite.
Okay. Okay, great. So is that?
Let us briefly talk about the LLMs, right? So I showed you the connection before, how these LLMs trained on log loss are essentially trying to approximate Solomonov, take, right? But that's the prediction part. How is up the action part? Okay.
Okay.
If you look at the action part, well, I mean, people use foundation models also for agents. And maybe the closest would be mu0, right? Where you take a learned model and then do planning on top of it. So instead of approximating Solonov by CDW, you could just approximate it by a large language model and then do Monte Carlo tree search on top of it. There are other ways, like, there's chain of thought and there's tree of thought, where, you roll out. It's a little bit similar to MCTS, right? You roll out various futures and then you get a tree, right? And then you decide what to do. So that would be a way to find a connection, right? And sort of mu0 is in a sense closed. It does the Monte Carlo tree search, which approximates expected max, and it uses mu0 doesn't use a language model, but uses other models. So if you would use a language model and then with mu0 style planning, then you could regard this, as a rather straightforward, I mean, not straightforward, but rather principled way of approximating the IC model.
So in the language model setting, what would be the reward?
You would also have as tokens rewards. There would be some tokens which are sort of related to reward. I mean, if it's discrete, it's just a reward 0 to 10 or something like this.
Oh, sorry. I mean, with like things like RLHF, you can have human raters give a feedback as to whether.
I'm not talking. RLHF is sort of barely RL, right? No, what you would here have is that the language model itself. So you train. Maybe I shouldn't call it language model, but sequence model or foundation model or whatever. Okay. So you are training the model of sequential data, which consists of actions, observations, and rewards.
Oh, okay. I see.
Yeah.
Okay.
And then it also predicts the observations and rewards. And then you just roll it out into the future and select a rollout where the rewards are high. Right?
I'm a little confused here. What's the problem you're trying to solve?
I'm trying to extend the current rather simplistic approximations of ICSI to larger model classes, and the largest model classes we now know, and the most predictors we have are currently large language models.
Oh, I see. Got it. Okay. That makes sense.
So you plug into ICSI, instead of Solomonov, you plug in a language model.
That's right.
Then you still have the Expectimax, but this you replace by Monte Carlo tree search like in zero.
Your psi, your C is now your LLM, essentially.
Yeah, exactly.
Yeah. Okay, got it. Okay, makes sense. Sorry. Yeah. Okay, yeah. I was confused with the notion of reward, thinking of RLHF, and okay, okay. Okay, I think we've
MC ICSI LLM. But this
so many
letters to be done.
It's like this almost looks like all, with the exception of maybe the A, it's all Roman letters. Okay, it's like a bunch of Roman numeral, like you're trying to write a large Roman numeral or something like that.
Yeah,
except for the A. The A throws it away. I don't know what number that is if you threw away the A, but okay. Anyways, too many capital letters. Okay, maybe one final thing as we close up. I know there's a final chapter or two in your book about philosophical aspects. Your book is quite philosophical in the sense that it's not just all, even though there is a lot of math, it ties it wherever there's relevant philosophy, you'll sort of make that correspondence. But you mentioned kind of at the beginning some historical context for the problem of induction. Famously, Hume and his predecessors have sort of, let's say, I don't know the right way to say it, but kind of cast doubt about the validity of induction. And then there's, more recent works like the Popper-Miller theorem about maybe various problems with the formalism of induction. To what extent do those perspectives, do they inform AXC or the other way around? What's the relationship between these?
Well, as far as I can tell and remember, Solomonov was influenced by Carnap's theory of induction, so Carnap's induction theory. And the Carnap theory was essentially, maybe he did more, but was essentially Laplace rule. But Laplace rule has the problem that it cannot confirm universal hypothesis. So if you ask what is the probability of the next bit being one given the history, you seem to get a reasonable answer. But if you ask what is the probability that all future will be one, like, you have seen 100 black ravens,
right?
What is either the probability that all future ravens are black or that the hypothesis all ravens are black true? If you solve that in the simple base Laplace model, you get probability 0. You don't even get probability, you get 0, which makes no sense, right? So you see 1 billion ravens, black ravens, and then it predicts the probability that all ravens are black is 0, right? So this model fails. And interestingly, at least from the technical literature I am aware of, most quantitative approaches fail on this task of quantifying or predicting so-called universal hypothesis or quantified hypothesis. And also Solomonov doesn't explicitly sort of consider this problem. I considered it later. Solomonov solves this problem. In one of my papers, the philosophical treatise of universal induction, I go through a couple of these philosophical questions and show how Solomonov solves them. There's the problem of zero priors. There is the more technical problem of reparametrization invariance. So this paper looks at a bunch of philosophical and statistical problems which most approaches have, and shows that Solomonov solves all of them.
Okay, actually, in this very specific case, I think what you're saying is the following. Suppose the observations you made are all ones. You've seen 1 billion once. Now, yes. there is a program which says, actually, my program is print all ones. And because it has positive weight on that, quite large weight, because that's a very simple program, then there is a positive probability that indeed all future digits will be 1, right?
Exactly. Yeah. It's as simple as this, right? It is simply done, right? And but interestingly, Laplace rule, Carnap's theory, and most of the other theories I'm aware of get it wrong.
I see. Although maybe it's a little unfair because with Laplace's rule, you're only allowed these Bernoulli predictors, and you're in such a small model class that maybe you. I mean, of course, technically you do have p equals 1 as a limiting point in your hypothesis class, so that you never select for it because you always have to have some margin of uncertainty, right?
I'm not even asking for selecting that p goes to 1. I mean, of course, ultimately we want that. If we see n ones and n tends to infinity, the probability of this hypothesis should go to 1. But I'm just asking that it's not 0.
Exactly. That's right. Yeah, that's right.
Even this most models get wrong.
That's it. Okay. I don't know enough about
the prediction part, and from the philosophical perspective. From the decision theoretic perspective, I mean, there is something like causal decision tree and evidential decision tree. There's also some philosophical paradoxes, and the Newcomb's paradox, and you can try to reason how I see what sort of deal with these paradoxes. I think these paradoxes are very fun, but they are rather irrelevant from a practical AGI perspective, because I mean that's not, you don't face this Newcomb type problem in practice, right? Because there is no omniscient person who can predict what you're doing and put it into. And if so, you have this differential problem and so on. I discussed that a little bit in one of my papers. But so I would think the deep philosophical aspects are in the induction and prediction part. The sequential decision part is sort of relatively solid.
Okay. Yeah, I don't know this Newcomb thing, but I know you mentioned it in your book, and I don't know enough about it, but maybe you could comment on it anyways. But there's something called the Popper-Miller theorem, which I only know very slightly about. I've read bits and fragments of it. My vague understanding is that it sort of presents some problematic issues with the way you do induction in a Bayesian setup. Are you familiar enough about it to say what it is and its relationship?
I will look it up, the Popper-Miller theorem. I mean, I know a little bit about the Popper's corroboration and falsification stuff and so on. And I mean, I guess he did it in the 1940s, and maybe that was good philosophy at the time, and definitely advertised it to the scientists well. We were maybe not aware of it, but I think the world needs to move on from Popper. There's a lot of out there now. But I mean, I will look up the Popper-Miller theory, this specific one. Maybe I knew it, but I forgot his name. So
I see. Okay. Anyways, I think we've definitely covered a lot. Thank you so much for your time, Marcus. This is a very fascinating subject, and I think, hopefully this will bring it to the attention of more people.